All right, it is often useful to talk about vectors in terms of its components. So to start this discussion, let's start in two-dimensional because it's easier to see. So if we take a vector A and we position its tail at the origin, then you can easily see that this vector right here, call it A, has both an x component and a y component. So if we say this distance is a1 and this distance is a2, then we can describe the vector A in terms of its components. And we use the triangular brackets a1, a2 to represent the vector that has these components, which describes both its magnitude and its direction. Okay, so similarly, if we're in 3 space, and we take our vector and we position it at the origin, then we see that it has both an x component, a y component, and a z component. So in this case, our vector A would be equal to a1, a2, a3. So it is often useful to describe our vector in terms of its components. All right, so if we look at 2 points in space, we'll say we're in 3 space, A and B. So A and B have respectively coordinates a1, a2, a3. So now we're talking about points and not vectors. And B has coordinates b1, b2, b3. Then we can describe the vector between the two, and it matters, right, which place we start our tail. So if our tail starts at A and ends at B, then we describe this vector as AB. If, however, we start our tail at B and end at A, then this describes the vector BA, which, as you notice, they have the same magnitude but opposite direction. Well, how do we determine that in terms of our components? Well, let's start with the vector AB. Let's switch back to that color so to be clear. So the way we're going to define the vector or compute the vector AB is we are going to subtract the components, but we're going to subtract the A components from the B components. So it would be B2 minus A1. Let's start that sentence all over again. It would be B1 minus A1. That would be the x component of this new vector. B2 minus A2 and B3 minus A3. So a lot of times students get that confused. So figure out a way to remember that if you're starting your tail at A and ending it at B, then you're going to subtract the A from the B. All right, and that's how you define the vector between A and B. Okay, another thing that components allow us to do is to talk about the magnitude of that vector. So again, let's go into 2 space because it's easier to see. So if we have a vector A, then we see that it has components A1 and A2. So we represent that vector A as triangular brackets A1, A2. Well, then we see that the magnitude or the distance of that vector, or the length of that vector, we can figure out from the quadratic formula. So the notation we use is the absolute value of that vector, and that's going to be equal to the square root of A1 squared plus A2 squared, just like we remember from a long time ago. Well, similarly, if we're in 3 space, let's see if we can sketch that drawing, and we have a vector A out there, then we can calculate that the magnitude of it is equal to the square root of A1 squared plus A2 squared plus A3 squared. Now we can see this is true if you remember back to our discussion about finding the distance between 2 points in 3 space. except this time our first point is the origin and our second point is the terminal point of our vector. Now, speaking of points and vectors, we can go backwards as well. So if we have, let's start in 2 space again, a point P, which we'll say is A1, A2, then we can describe a very particular vector that starts at the origin and its terminal point is our point P. And we actually call that the position vector of our point. All right, so P is our point, but we could describe the position vector to be the one whose components are the very coordinates of P. So, likewise, if we're in 3 space and we have a point in 3 space, we'll say this time A1, A2, A3, then we can describe the position vector to be the one whose components are exactly A1, A2, and A3.